So welcome, Joe. Do you want to start by telling us what aspects of string theory should cosmologists be thinking about in 2023?
The thing I think in string theory is most interesting for cosmology is the way it's got the potential to undercut what one sometimes thinks of as the standard cosmology. The standard cosmology, it normally has this picture that you have inflation, then you have reheating, and then you have this long period of radiation domination, which eventually turns into the hot Big Bang. And one of the most generic features of string theory has always been that string theory has extra dimensions, and the legacies of these extra dimensions in 4 dimensions are scalar particles, are massive scalar particles called moduli, which typically interact with gravitational strength couplings. And the reason for this is what they are physically is they are the descendants of the higher dimensional modes of the graviton. So you have the graviton in 10 dimensions. This comes down to 4 dimensions, and this gives you scalar fields. And these moduli, I think, are one of the most interesting things. If you're a cosmologist, these are the single most interesting things that string theory gives you. And the reason for this is because they're scalars and they hang around for a long time. So these have a very powerful ability to undercut what you may think would normally happen in cosmology, because if you have long periods of radiation domination and you've got any of these scalars hanging around, they will just continue to hang around, for example, and they will come and dominate the energy density of the universe. And then they will take you away from what you think is your long period of radiation domination. So if the quick answer, if you think what is the most interesting thing in string theory for cosmologists to think about, is moduli. Gravitationally coupled scalar fields.
And even if it's only 10 dimensions down to 4 dimensions, obviously 10 minus 4 is 6, but the number of moduli that are possible is much larger than 6, because the geometry is much more complicated in 10 dimensions than 4 dimensions. Is that right?
Yeah, that's absolutely right, Sean. So that the way you count the number of moduli often ties to the topology of the extra dimensions. So it often corresponds to, so if you have, depending on how, if you have these Calabi-Yau geometries, they're what's called the Hodge numbers. But one way of thinking of these is they're sort of like the holes in the extra. They're generalizations of the thing that if you have something like the kind of bagel shape and you've got 2 separate ways you can wrap around it, it's the generalization of that. And as you can imagine, when you go to 6 dimensions, these can be very complex, and there can be many different analogues of these. And so the moduli can then come, there can be hundreds of moduli, for example, when you compactify down to 4 dimensions.
What you were talking about sounds like the sort of thing that someone who wants an early dark energy model might be very excited about, because this evidence that it might alleviate in some ways this Hubble tension, and obviously it also has other interesting possible things, but an early dark energy period would be exactly a consequence of a moduli floating around for a little while and then dissipating as the universe cooled.
So I suppose by early you mean, because I suppose inflation is obviously an early dark energy period by itself. Yeah.
Sure. I guess early being, I think, to solve the Hubble tension, or not solve, but to have an impact on the Hubble tension, it has to be early dark energy, very close to when the cosmic microwave background is forming, so close to the last scattering.
Yeah, I mean, I think scalar fields are the quantities that are capable of evolve, that can give you dark energy that then ceases to be dark energy, as we know during inflation. I mean, that's the kind of the basic what inflation is. That inflation is dark energy that then ceases to be dark energy.
Okay, if there are only 2 to 3 things that people remember from the review article or this video, say 12 months from now, what would you want them to be?
So this will reflect my own biases. So what one is, I think, illustrated figure 21, which is on page 81. This idea you can have a long period of moduli domination. I mean, you could have, between something like just before BBN, so up to 10 to the minus 5 seconds or something, and all the way from potentially from the period of around inflation, that you could have the universe dominated by the energy density of moduli fields. So this is, on a logarithmic scale, this is like half the age of this could be like half the age of the universe. So you could have a really enormous period where the universe, the actual principal component of the energy density of the universe, are the moduli fields from string theory dominating the energy density of the universe. So that's number one.
And this is after inflation and after reheating.
After inflation and before BBN. Yeah. So this is the point that because if you go to reheating and you fill with radiation, but if you've got any scalars there, the scalars will then just dominate back over the radiation because they redshift slower. And so you can fill the universe with moduli very easily. The second point is that there is this really interesting connection between the ability to go transplanckian, which is then as you know, which relates to the kind of the magnitude of tensor perturbations during inflation. There, I think, is growing evidence that it's hard to go transplanckian in string theory and keep the potential flat. And the third thing is that you can have reheating dominated by moduli, in which case the thing that actually reheats you are the moduli. So then the decay modes, the branching modes, and moduli actually dominate can dominate reheating. So those are the things to my personal perspective, is most interesting about string theory in cosmology.
Okay, so let's get into some motivation. String theory, at least in 2023, has become a little controversial in some fields, maybe more so out of actual cosmologists and scientists than inside. But do your best, motivate why should cosmologists care about string theory in 2023?
So cosmologists, I think, go into cosmology because they care about fundamental physics. They don't go into cosmology to make lots of money. They don't go into cosmology because they want to kind of do some spin out company that they're going to use their techniques for. I mean, they're cosmologists, I think, do cosmology because they want the truth about the universe. And so string theory is our best candidate theory of gravity on the most fundamental scales. I mean, cosmology is a subject where gravity matters, where dynamical gravity matters, where gravity on the very early universe, where the energies are extremely high, where the energies can be up to 10 to the 16 GeV to the 4th in the case of inflation. So the reasons cosmologists should be interested in string theory is because cosmologists want the truth about the universe, and string theory is definitely our best candidate for a quantum theory of gravity that also incorporates and makes contact with particle physics in all its ways. And I talk for ages about why string theory is the best candidate of gravity, but I don't know whether that's really the...
You did literally write the book, Why String Theory.
Yeah, I did write a book about it. Well, it's kind of sad because the bit that... Well, no, it's not sad, but the bit that always goes viral is the chapter 7, which is direct experimental evidence for string theory, and deliberately it's just like a single sentence saying there is no direct experimental evidence for string theory. Yeah. But it's about being honest about, that physics is an experimental subject. And I think we've got lots of indirect evidence that string theory is correct, but we do not have any direct empirical result.
Yeah, I'm reminded often of when people worry about direct evidence for string theory and other things, of how long it's taken to build, I don't know, some cathedrals in the world, hundreds and hundreds of years. And it didn't mean that the people who started building the cathedral shouldn't have started building the cathedral, because eventually the cathedral got finished. And I guess it's a little similar here. If we're still around 200 years from now, maybe then they will have direct evidence for string theory, but that doesn't mean we shouldn't be working on it now.
Yeah, it's not the subject. You don't go into fundamental physics as you expect it to be. You're guaranteed to get all the answers in 20 years. I mean, I think so. The question is what added value does string theory? I mean, I think the fair question to always ask is why care about string? Why not just do cosmology with kind of quantum field theory? What added value does string theory give? And to me, moduli are one of the main added values, because you can include them in just regular effective field theory, but string theory really very strongly motivates the existence of particles that are scalars, that are massive, and all of whom's couplings are at gravitational strength. So they're incredibly, incredibly weak. And cosmology here is completely the inverse to colliders, because in colliders, particles which only interact gravitationally are totally irrelevant. You never make them. Whereas cosmology, it's always the other way around, because if you make them at all in the early universe, they will just hang around, because just the nature of particles who only interact gravitational strength is they don't decay, or they take ages to decay. So this means that even if you have lots of models of inflation which involve very rapid perturbative reheating, a very rapid transfer of energy from the inflaton to everything else. But if you have any of the moduli around at all, and they're actually there, they'll hang around. They're scalars. Scalars win over radiation. I know this is a really simple point for cosmologists, that matter goes as 1 over a cubed and radiation goes as 1 over 2a to the 4. But it's kind of profound, because if you have stuff with really, really long lifetimes and no matter, they just win. And they just, that extra factor of A is the universe, and they just win, and they just come to dominate. And then you end up completely filled with these particles. The
reason why this is not immediately ruling out all of the string theory is that you mean they dominate, but then once they dominate, they do then
decay. Yeah. Then they'll trouble. Yeah.
Or is it just like what you've got with inflation? They don't so much decay into other particles, but they just then roll down their potential.
So eventually, they can do two things. They can you can things, but once they get close to the minimum, they are just particles, and they do decay. But the thing is, if you've got but they can live so long. So if they live until 10⁻⁵
Which is long in the early universe, but not very long today. I see.
So as long as you reheat before BBN, and this is one thing I think really does motivate cosmologists thinking about low reheating scenarios, and thinking about how you would, if you want to do baryogenesis, for example, how do you do that if you reheat to 1 GeV? Because a lot of the standard scenarios are things like thermal leptogenesis and so on, which rely on reheating to often extremely high temperatures of 10 to the 11 GeV, and so they just don't work if you reheat to 100 MeV or 1 GeV.
And then let's say that you're a cosmologist who works on measuring the locations of galaxies in the nearby universe. Is the argument to them that all of these extra particles that were there after inflation and before BBN have left subtle impacts on correlation functions?
Okay, so this is the question. What one would one would hope. Now, how one would go from the hope to the reality is another thing. But let me sort of put one thing here, which I think definitely is relevant. So in the standard cosmology, the equation of state of the universe between inflation and reheating is basically is radiation. In stringy cosmologies, this is almost always kind of not true. You have periods of moduli domination. You have long periods of conation because these scalar fields they're on potentials, so they can roll down potentials. They can conate. So you can have substantial variations to the equation of state of the universe in this period between inflation and BBM. And this one, this is what one then would hope. But this is now more of a hope. I'm not going to give you a thing saying this is the definitive signature of this, but it strongly motivates significant changes in significant changes in the equation of state of the universe in that period. And then if you've got a way to probe that in the present universe, but that's the hard bit. I think that's more of a straight cosmology question, how you probe the equation of state, because with inflation we look at the C and B, but this epoch is kind of ultra small scale, so it's hard to do with measuring galaxies. So the question of how you do probe that epoch, but that is definitely a straight cosmology question, how you probe that epoch. Yeah.
Okay, so maybe even if we've got very sensitive gravitational wave detectors in the future, if we're trying to get to these kind of small scales.
Well, one thing in relation to moduli and moduli reheating, which I think is something I like, and I think it's also worth putting out as a sort of for cosmologists to be aware. So with normal cosmology, the earliest we can see back directly is the CMB, because that's basically that's loss the photo before that one, that's where last scattering occurred. But so if you have something like moduli reheating, so the whole point is because moduli couple with broadly gravitational strength, so when they decay, they can decay not just to visible sector particles, but they can also decay to particles that would be more hidden sector, and such like particles like axion-like particles, principal gravitrons. So there's other more or less hidden particles you could decay to. And the point is that if you decay to particles which is kind of hidden sector ones, then they can just propagate more or less freely through the universe. So this would be equation something like 247, for example, pages like 96 here. And if they can propagate freely, so as to propagate from the time of when moduli decay, then you could have some hidden sector. So this is something we called a cosmic axion background. The idea you could have like relativistic axions that were produced at the time of moduli decay, so like 10 to the minus 6 seconds, and have propagated freely since then, as a kind of a subdominant kind of dark radiation contribution. So this is the possibility that if this existed, this motivates the possibility of a dark analog to the CMB, except dating at much, much earliest times in the universe, before BBN, which, if such a thing did exist, and if one could ultimately detect it, would be a much earlier direct window on the universe. And this, again, I think is coming to physics of moduli, because moduli are gravitationally coupled. When they decay, they can also go to sectors that are, more or less invisible, and do not interact with the standard model.
Yeah, okay, let's maybe have a deeper dive now into a few subtopics that you think cosmologists should be particularly interested in. So do you want to name the first one and then give us a short summary of it, and then we can get into the weeds about that topic?
Let's go back to the question of inflation. So this is something that I think the significance of string theory here is reasonably well known, but I think it's still a good thing to talk about. So as we know, inflation involves scalar fields, and the inflationary potential has to be flat in order for inflation to work. But this is something where if you want to control corrections, so if you want to control corrections to the inflationary potential by operators which are again suppressed by 1 over m Planck, so this would be like 4.11, like 100 equation 138. So if you don't understand anything about quantum gravity, you've got no good reason not to just add to the potential a term like equation 139 to say you have your potential. So in effective field theory, you can just add terms that are higher order suppressed by the cutoff, and so you just add those to the potential. There's no reason you can forbid those. But then the problem is that these give you corrections to eta that are, broadly you expect to be order 1, which would then spoil your inflationary potential.
Eta being the slow roll parameter in the equation above that.
Yes, eta being the slow roll parameter. So to guarantee that your inflationary potential is flat, you need to be able to understand and control additional operators which are suppressed by powers of 1 over m Planck. And so we've got ineffective field theory that the suppressing by a scale, this is the scale of the theory you need to understand. So if we do Fermi theory, we have operators suppressed by the weak scale, and the way you understand those is you understand electroweak theory, and then you can compute these operators from first principle, and you can actually control the operators suppressed by 1 over m weak, or 1 over the W mass. So if we're doing gravity, where we want to be able to control operators suppressed by 1 over m Planck, we need a theory of gravity. So this is the thing that in inflation, if you don't understand your theory of gravity, of course you don't understand your theory of inflation. That if you're just trying to do, you just want to be a field theorist and you just want a field theory model of inflation, but then how do you argue that this is actually controlled? How do you argue that this is protected against corrections from some theory of the Planck scale that you don't fully understand? And the problem is you can't really.
And the reason why this is relevant to inflation, because you're not making the argument that in order to understand the gravity in the solar system, we need to understand, we can understand nuclear physics and we can talk about the sun without having to understand quantum gravity, even though the sun, I don't actually know stellar physics that well, but I'm pretty sure that you have to include gravity to get, the rate of fusion inside the sun. So what is special about inflation here that is saying, okay, we've got field theory and we've got gravity, but we actually need not quantum gravity, but fundamental gravity.
Yeah. So normally, you would say that if you have your whatever physics you're doing, say, in the solar system, and you add additional operators suppressed by additional powers of 1 over m Planck, then they're just completely irrelevant because, for example, if you've got a momentum expansion and you're adding extra things which are kind of momentum divided by m Planck, and you're just adding a kind of higher terms to that, well, they're just, each one is progressively smaller, and so they are kind of not just, they're just so small, tiny corrections to your kind of leading physics that they are, that's why you can ignore. That's why it's not so much we say you can't do quantum gravity at low energy. It's in the language of effective field theory, the corrections are all irrelevant, so they're just irrelevant, so it doesn't matter. It's not that's why it's not a problem at low energies.
And then the problem with inflation then, because it's still not Planckian energy.
No, it's not Planckian energies, but so if you look at just equation 139, for example, and so you have some potential, which is you want to be your inflationary potential. And then you say, well, if I add an operator to it, so suppose, but I don't understand the operators suppressed by 1 over m Planck. So I just parameterize this by some constant c, but this is definitely a an operator. There are extra powers of M Planck in the denominator. But the point about this is that such operators, they change if the constant is order 1, they will change the slow roll. They would change the slow roll condition as long by a kind of order one fact. And so the slow roll condition, which is kind of an integral part of your model of inflation, then is kind of fails with these higher order operators.
Why, if you have some, I don't know, model of inflation that's coming from some extended Higgs model, where you can just write out your potential, where everything's kind of under control within that model, why they should be worried about that model doesn't care about string theory.
Okay, so yes, I guess so. Whatever model you've got, and you say, well, let me so if you whatever your inflaton field in that model is, so if I then add to that model that potential a term which is, so like this term in 139, which is basically inflaton over M Planck squared.
Okay, so you say over M Planck squared, 139 does have a lambda there that you then say below it is less than M Planck.
Well, so if the constant is around order 1, so this constant C is order 1, then it will give you, so if we look in 140, you see that if lambda is about M Planck and C is about 1, then the slow roll parameter becomes order 1, which means so you either need to say that C is very small, but then there's that question of, well, why should C be small? Because if this is generated at the Planck scale, the natural effective field theory the natural effective field theory expectation is that C will be around 1.
Mm-hmm, mm-hmm, mm-hmm. And this is because the eta parameter has these two derivatives with respect to phi. So if I add a term that looks like 139, which seems totally natural to add a quadratic term, then when I take two derivatives of that, the v prime prime, no matter how small I've made phi's disappeared from my formula now. So long as C is of order 1 and lambda is of order M Planck, the contribution to this eta parameter is of order 1. I see. Okay.
Yeah, and so you've got to kind of, so you need to have some way you can control operators that are suppressed by powers of M Planck.
So your model has to explain why C is a very small value, I guess.
Yeah, so now you can just say, well, I'm not going to care about these. I'm a field theorist, and by definition, I'm just going to ignore all these operators. Okay, and that's perfectly fine. And as we know, inflation has been kind of is a paradigm in search for theory. And so you can just take these ad hoc inflationary potentials and just say, this is my model. But if you want to kind of really understand really understand this model and say, well, or any model, and say, how is this actually controlled? Then you need some theory of how you control operators that are suppressed by M Planck. And then that's a question about string theory, or about, more generally, it doesn't have to be string theory, but a question about quantum gravity.
And the reason why this is kind of not a problem for all of these future potential, periods of modular domination is that they can all just have eta equals 1. Essentially, inflation has the problem that we've sort of observed eta and it's much less than 1. And so we have to explain why our observation is actually true. That you need inflation to last for a long time.
Yeah, assuming that the inflation is true. Yeah, then assuming inflation is true, then yes, and inflation is to last for a long time, then we need to understand why such operators are absent. And so it could be because you've got a theory of the Planck scale, and there's some structure there. There could be some symmetries there. There could be just luck. The constant C just happens to be really small. It's just fine-tuned small for some reason. But wherever it is, it's a question that, if you want to fully understand what's going on, you need to answer.
Okay. So this is, I guess, so very relevant for people who are cosmologists who are building inflation models, that this is something that, in principle, they should worry about, but in practice, might not. You have to do one thing at a time. So I guess you could build your model and then start worrying about this after that.
Yeah. So another related question with inflation is this question of transplanckian field excursions. So this is this carries on. This is on 141, 142, and so as I think is kind of quite well known, the large values of the tensor to scalar ratio in normal circumstances correspond to transplanckian to field excursions of the inflaton, where the inflaton goes through something like roughly a Planckian distance in field space. And so the upshot is that if you're going to have large R, you end up then that the field moving close to a kind of Planckian distance in field space. So then what this means is, and as soon as you, as a string theorist, as soon as you see M Planck, your eyes light up because you think, this is me. This is where I come in. And the point is that it actually turns out to be quite tricky to have potentials which are flat over Planckian distances in field space. This is a subject that's been kind of gone around for quite a long time. It's received a lot more attention with the sort of it's been this sort of the sort of various swampland conjectures that have occurred in the last few years, where the idea like the sort of there's something called the swampland distance conjecture, which is the idea that as you go through Planckian or distances in field space, you get kind of towers of field that get exponentially light, and so. While one M Planck, but then really extend this out and say that you've got towers of field that get exponentially light for every kind of Planckian distance you go in, it then becomes very hard to sustain a flat potential if you've got huge towers of fields that are kind of changing their masses by exponential amounts, but you want the potential to just remain flat or very close to flat. So this is a topic that has been kind of there's a sort of theoretical question about string theory here: is can you have potentials that are flat and positive? I mean, of course, you can have potentials that are flat and zero across transplanckian distances. This is not an issue. But can you have potentials that are flat and roughly de Sitter across substantially transplanckian distances? And so this is a kind of if you like, this is by itself, that's a question just about kind of gravity and quantum gravity. But what is very kind of interesting, here is this, in terms of inflation, this is something that actually then maps on to something which is observable. I mean, while we're not going to observe values of R significantly bigger than 0.01, because if that was going to happen, it would have already happened, and such values are kind of ruled out now. But they certainly could have been observed, and even if R is ever measured, as non-zero, or measured in the foreseeable future as non-zero, then it would mean that you would have a field range which was either Planckian or close to Planckian. And that just would be, and that would be very, very interesting, because that would be something which is involving a field moving through the Planck scale. And again, the only way to have a flat potential is you have to control all the transplanckian operators, the operators which are in here in 142 of fields suppressed by multiple powers of the Planck scale.
There are these kind of constructions of intricate potentials such that delta phi, like it can move a large distance in delta phi, but stay quite a small value by kind of winding around something, so that the absolute value of phi is not getting big. Is that done in such a way that is satisfying, or are there kind of holes in that thinking?
So these are kind of what's called Modular models. Yeah, and the view you kind of get on how it would kind of depend on who you talk to in terms of thing. But I think it's a fair comment. There are challenges in all ways of going transplanckian, and the more you want to go transplanckian, of a theoretical point, the bigger the challenge is. Like no one in string theory is going to, if someone says, well, if someone says, I don't think you can go transplanckian, no one's going to really be arguing by this whether you mean, oh, you can't go half a transplanckian or 2 times M Planck, or pi times. I mean, the question of where the factors of pi are or where the factors of 2 are is obviously a very one. But the question of kind of, could you go 100 M Planck and keep it flat? I mean, I think this is exceedingly difficult. But then the question of whether this, whether difficulties going transplanckian means it's difficulties going, pi times M Planck or, a 10th times M Planck. That, I mean, I think that is very. I mean, all these distance conjectures, there tends to be this order 1 factor that comes in front of M Planck in terms of how far you can go. But this is I think something which is one of the very few things where you've got this intersection between what is something which is genuinely observable, and observable with today's technology, and some of the most kind of abstract questions, what are really abstract questions about quantum gravity and what can or cannot be achieved in a quantum theory of gravity. And this is almost the only example I know where you've got this kind of actual connection.
And not, say, things like bispectra, trispectra, etc. of CMB correlation functions, where if during inflation there were extra degrees of freedom, they might have impacted these observables, or could I suppose in principle that could be nothing to do with string theory. It could just be a quantum field theory with an extra particle or something.
Yeah, so that's why I say this one. I think the question of field excursions is the one which is most closely tied, because this has really got the factor of M Planck in, and so the factor of M Planck really means that this is the where kind of string theory kind of, or other theories of quantum gravity would kind of come into their own domain.
So you mentioned swampland conjectures earlier. Do you want to have an opinion about what a non-string theory cosmologist who's writing down, quantum field theory models, should they be caring whether their essentially effective field theory model is or is not in the swampland, or should they not care?
So it depends. I think depends which conjecture. So there are, I think the conjectures vary between ones where there's a kind of a lot of support and ones which are very speculative. I think ones which are so something like the distance conjecture. So I think this is one where there's a lot of support.
Which is the one that you've just been talking about?
Yeah, in the version which has the most support is that if you move substantially transplancking distance in field space, then towers of fields will come down and become light. And if you head out to the boundaries of modulo space, then basically is where you're moving the parametrically transplanking distance in field space, you will get extra towers of fields that become exponentially light.
There's this other one then, I guess, that de Sitter vacuums aren't possible.
Yes, so that one starts with a very strong statement that you couldn't have de Sitter critical points, and then it kind of modulated into a thing which was maybe sort of, well, you can have critical points as long as they're not too flat. It does exist in a form that you can't have de Sitter vacua, but then it's very hard to actually get solid purchase on it, or to get solid evidence for it, other than the fact that we already know that constructing fully explicit de Sitter vacua is hard. The weak gravity conjecture was also the Conlon conjecture, where there's an awful lot of support, but that is for cosmologists that is probably less relevant. I mean, it can be useful to cosmology, but because it's normally applying with when you've got U1 fields around. And obviously there are lots of cosmology models where you don't have extra U1 fields. You don't need extra U1 fields to be thinking about inflation or to be thinking about the cosmological dynamics of the universe.
I remember there was also one swampland conjecture that seemed to have like the V prime of a potential that had to be bigger than something, like, which impacted inflation certainly. And
yes, I mean, I think this is one of these ones. It'd be if it was true, it would have huge implications. But I don't think there's a sort of...
Because it would sort of imply that today we must be in some sort of quintessence model, even, like it can't be a...
Yeah, I don't think there's strong evidence for it.
Have you got thoughts about, what string cosmology might look like in 10 years? Because that might be an interesting...
Yeah, I mean, let me throw the sort of left field thing on string cosmology, but which is the possibility that you could, which is not ruled out at all, is that you could actually have fundamental superstrings in today's universe. I mean, cosmic strings as a idea are less popular than they were, but the bounds on the attention. I mean, there are lots of string models where the fundamental string scale is much less than the Planck scale, and so I think once you get below about G mu being about 10 to the minus 7, for this corresponding to the tension of the strings, these things are not really constrained. So the sort of left field idea, which it's not fashionable, but doesn't mean it can't be true, is that you could have actual fundamental real superstring, not sort of just virtual ones or thing, but actually real superstrings stretching across the universe. So I mean, I think one shouldn't forget this. One shouldn't forget this because it could be true.
Super naively from the outside, I find that baffling, because if they're that long, maybe this is a really naive thing to say, but if they're that long, then if the string length is universe size, how can a quark be ultimately made up of strings? Is that like making remote sense as a question?
So the quarks are kind of like the quantum excitations. So these are like classical strings. but these are classical superstrings. So this is in the same way that kind of the cosmic strings that because Kibble you had like Kibble this idea of cosmic strings, cosmic field theory strings, but that one can also have cosmic superstrings.
I see. So it's a classical string that would still have a quantum excitation that would be very small.
Yes, and this is the idea. I mean, that people worked a lot in cosmic strings at one point, and then inflation came. So cosmic strings aren't the origin of structure, but cosmic strings could exist, and so people have worked on these sort of ideas of these string networks. And so I think the idea one shouldn't forget is the possibility that real superstrings could really be out there.
Oh well, that'd be exciting. What would be the way to continue looking?
I think things like was it pulsar networks and gravitational waves from them are the so the general question is like, how with any string network, how do you push g mu down below about 10 to the minus 7? I think microlensing is the way people have pushed, which is where the maximum current bounds are. How do you extend that? And I think it's things like pulsar timing arrays are the ways. I'm not an expert on these, but I think those are the things the plans, the hope is to push g mu even lower.
And the reason why microlensing is the constraint here is that because the superstring is somehow gravitational, if it passes between us, when a lensing event is happening, if there's a string also there, you'd get like glitches to the microlensing event, or would the string itself do the microlensing? Or
I think I think it's that the string doing the lensing. I think, I'm not an expert on where the bounds, but I think it's the string doing lensing. But that could be.
Okay. And then I guess with the pulsar timing array, it would be the same sort of idea that somehow the
I think things like the gravity, because I think if you've got strings, then because they're constantly radiating energy through gravitational waves, and so then I think it's the idea that the gravitational waves they're constantly radiating are what you would be sensitive to, and the bigger the tension of the strings, the stronger the waves.
Okay, and we would be able to tell these kind of fundamental superstrings apart from just like some sort of topological string, or would it be that you would detect something and then you would wait and find out what it is?
I think it's that.
Okay, yeah. Well, what work being done in cosmology at the moment do you think is particularly underappreciated by the rest of the community?
So I think in this sort of I stick to the more stringy cosmology, I think, which I think the bit is the way that in string theory this changes in the equation of state in the universe between inflation and BBN, because they will happen basically they will almost happen in string cosmology. So I think these deserve to be better studied in terms of how you would detect that the equation of state in this period was different.